Chapter 7, Part 2, Interpretations of Quantum Mechanics. Though the measurement problem in quantum mechanics calls attention to the possibility that the observer, indeed, the very consciousness of an observer, has an effect on matter even as the observer perceives those effects. There are other avenues that physicists have explored in their efforts to understand the paradoxes in quantum mechanics and resolve this measurement problem. There are four principal explanations or interpretations, as they are called, of quantum mechanics. Certainly, all four of these interpretations cannot be true, but each has something to offer us. Language is not adequate to describe in a few breaths the many facets of reality, so to achieve a broader understanding of nature, we need to know each of these interpretations of quantum theory. We have already met the first of these four interpretations of quantum mechanics, the Copenhagen interpretation. The second has a rather fancy name, the stochastic ensemble interpretation. The third understanding of quantum mechanics is rather abstrusely labeled the relative state interpretation, although it is more popularly known as the many worlds interpretation. The fourth is mysteriously dubbed the hidden variable interpretation, or perhaps interpretations is more accurate here. These interpretations take many forms, but nearly all efforts to solve the measurement problem can be placed in one of these four categories. Let us look at each of these in turn. The Copenhagen interpretation. Although we discussed the Copenhagen interpretation earlier in this chapter, it does have variant forms that are worth mentioning. Fundamentally, this way of understanding quantum mechanics accepts the original idea of a superposition of states given by wave function that develops immediately after any interaction between two or more bodies on the atomic level. The resulting system exists, at least for a while, as a collection of possible states, as fuzzy, unresolved potentiality, a collection of many possible things that it can become and from which it will ultimately become is somehow chosen. Various mechanisms have been suggested to explain how the transition, the state vector collapse, or the reduction of the wave function actually occurs. The patent explanation is that the state vector collapse happens on measurement. The trouble with this explanation is that the measuring apparatus is, after all, just another piece of physical matter interacting with the system to be measured. As we have seen, many physicists, such as von Neumann and Wigner, as well as opponents of this conventional understanding of quantum mechanics, such as Hooker and Einstein, have argued that quantum mechanics is saying that it is not the measuring apparatus as such, but rather our observation, our consciousness, our mind, that brings about this change. Others have suggested that the change takes place naturally as we make the transition from the microscopic world to the macroscopic world. After all, is quantum mechanics not the physics of the atoms? And did not Paul Ehrenfest prove that for large objects, quantum mechanics says the same thing that Newton's mechanics says? This is surely a good argument. If quantum mechanics agrees with Newton's equations, when we get to the macro world, then the problem will surely all go away. And Ehrenfest did prove a very important theorem about quantum mechanics merging into that large-scale physics of Isaac Newton. But Ehrenfest did not say that the macroscopic physics described by quantum mechanics is the same thing as Newton's classical physics. He only showed that quantum mechanics becomes that classical common sense world and certain kinds of transitions from the micro to the macro world. He showed how quantum mechanics, when applied to large objects, would generally yield a description like the one Newton's equations give. But many physicists have overlooked the fine print. Ehrenfest's theorem does not hold for the instruments we use to peer into the atomic world, and it does not hold for other macro world events that depend in a strong way on microscopic fluctuations, perturbations, and contingencies that can affect our large scale world of everyday life. Quantum mechanics must reach into the macro world too. If Ehrenfest really had proved that quantum mechanics becomes the same thing as Newtonian mechanics in the everyday world, then we could never even have known about quantum mechanics. There would be no quantum theory. Thus, this explanation, this way out of the measurement problem, does not work. We have already seen that simply bringing more and more interactions and more complexity into play does not lead to a simpler result either. We do not get rid of the many potential states by letting our original system interact with another system, for example, a measuring device. That was the whole point of von Neumann's study of the measurement problem, where he looked at each step from the events at the atomic level all the way into the brain without ever finding a place where the Schrödinger equation would suddenly, or gradually for that matter, converge into a single event explaining why we see only one state when we observe the world. Despite this, buzzword explanations of how quantum mechanics works are still heard coming from the lips of even some of the most distinguished of scientists. The stochastic ensemble interpretation. We have seen that quantum mechanics began as simply a statistical theory of matter. The theory initially said that matter is rather like dice and that some things are predictable and other things are not. It can tell us what photon energies could be emitted by an atom, for example, but in general it cannot predict energy in the moment of emission for any specific photon from a specific atom in an excited state. We also run into trouble when we try to use quantum theory to visualize what exists just before we make a measurement. However, the stochastic ensemble interpretation, that is quite literally the collection of random happenings interpretation, says that such a question is meaningless. It says there is no superposition of states, no potentialities. There is simply the measurement event. And it says each event is simply a sampling from a collection, an ensemble of experiments done exactly the same way. All that really exists is the ensemble, the collection of results we get when we do a lot of experiments. All that physics can do is say what experiment is performed and use Schrödinger's equation to give a description of the ensemble. This ensemble does not require the existence of potentialities, according to this interpretation, but instead it claims simply that quantum theory gives a description of all the results we would see if we carried out a very large number of tests. Then we do the experiment. That experiment is just one event taken out of the total collection of things that will happen. Where the Copenhagen interpretation speaks about what exists before a measurement, the stochastic ensemble speaks to the question as though nothing exists except the collection of results we accumulate as we do more and more experiments. It is probably okay to focus our attention on what comes out of the actual experiment, but what is an experiment? More precisely, what distinguishes an experimental interaction from any other physical interaction? In reality, what distinguishes it is the fact that we, as conscious beings, identify the measurement apparatus as such. that has meaning to us, whereas other events that occur in a complex interaction would have no such meaning to us. The ensemblists do not define measurement, that we intuitively know which processes are measurement events and which are not is so obvious that it seems unnecessary to acknowledge. As a result, the advocates of this interpretation seem to solve the problem von Neumann posed. You remember, it is the problem about where we break that continuous chain of interactions between the atomic process and the conscious brain. The ensemblists break off the sequence at the measuring device. The real issue of the measurement problem is consequently hidden in a clever shell game shuffle. The issue in quantum theory was never about quantum mechanical events being stochastic. The problem was that a measurement no more did anything new than did the original interaction. Measurement, quote unquote, is just a way of anthropomorphizing one of the interactions. If that is allowed, then one can use the stochastic ensemble interpretation to deny reality to the physical system being measured, so that one can no longer say wave function is a collection of potentialities. But unless one can complete that task by defining measurement in some unique way, the measurement event itself must be denied existence by the same logic. If the stochastic ensemble interpretation denies any existence to potentialities and does not tell us what is new about measurement that cannot be described by the Schrödinger equation, then measurement as something that gives us the sampling does not exist either. More than this, Wigner has offered a specific example in which an interaction plus a measuring device that gives one result can be turned into an entirely new experiment in which the measuring device of the original setup becomes part of the experimental interaction, just a part of an interaction subjected to a further measuring device. In Wigner's new experiment, the arrangement leads to an entirely different experimental outcome. This is known as Wigner's double Stern-Gerlach experiment. In the double Stern-Gerlach experiment, neutral particles, atoms, say that have magnetic moments, quote unquote, they act like little magnets, are directed in a beam toward the two poles of a strong magnet. The experiment is set up so that all the magnetic moments of the atom initially point up. Now let us look at these atoms one by one as they go in and come out from between the poles of the magnet that lies in the horizontal plane. As these atoms enter the magnetic field, the atoms will be flipped, just as a compass needle will flip when placed near a magnet. Because the magnetic field is perpendicular to the direction in which the atoms originally pointed, they can flip into the horizontal direction, pointing either right or left. Either with or against the magnetic field, either can happen. Now we can carry out a measurement with a measuring device to find out which way the magnetic atoms flipped. To do this, we let the atoms travel through a second magnet's field that is designed to be very divergent. This causes the atom to drift in the direction in which their magnetic moments now point, forming two separate beams. By placing detectors on either side of the atom's path, we can see which way each atom has been deflected and in which direction each atom's magnet points. But there is something else that we can do. We can let the atom travel farther past a wire carrying an electric current set up with just the right current in it to produce another magnetic field to deflect again the atoms of the two beams, bringing them back to form a single beam once more. This field will again flip the atoms in a direction perpendicular to the prior right or left directions. We can then again analyze this beam to see whether the atoms are pointed sometimes up and sometimes down, or whether all the atoms now have their magnetic fields pointing up as they originally did. You might think that because the first magnet caused them to flip randomly to the right or left, making a random 90-degree flip, the second magnetic field from the wire would cause them to flip randomly, also flipping them so they point up or down at random. You might think that when recombined, they would again be randomly deflected up or down, but orthodox quantum theory tells us they will all point up. Now, at one point along the way, we put a device, a divergent field magnet, to interact with the beams so as to separate out the atoms according to their magnetic alignment. That is to say, we did something very much like doing a measurement. If we had stopped there, then according to conventional physics logic, that would have to be the complete interaction. That would have defined the ensemble, including the measuring apparatus used to sort out left and right pointing atoms. However, if we let the beam go on to be recombined by the current loop and then to a third magnet to see which way the atoms are then aligned, we would find that the second magnet, which previously defined the measurement apparatus and also the ensemble, no longer defines what the ensemble is or what a measurement is either. Hence, we are forced to ask ourselves, what is it physically that means we cannot simply treat the first magnet as the interaction and everything after that as the measuring device? Moreover, in any experiment, if we make our restoring current loop sufficiently elaborate, we can always add on more stuff that will turn what originally looked like a completed measurement into only the first half of an interaction. In practice, of course, we can do such things only for the simplest kinds of interactions, but in principle, it could always be done. This means that we know where the experiment ends, not by means of any physical theorem, but only because we use the word experiment anthropomorphically. Because of this, the stochastic ensemble interpretation is a shell game that works because it sneaks the observer in by using the word experiment to delineate what the ensembles are. Still, we will see much later that it does help give us a piece of the answer. It does focus on the measurement event, telling us that if we could define that process, we might just be able to solve the measurement problem. The answer, as we will see, will reveal much about the nature of reality. Everett's Many Worlds. Back in 1957, a graduate student of John Wheeler's at Princeton submitted a doctoral thesis on something he called the relative state formulation of quantum mechanics. In his thesis, Hugh Everett III suggested that there might be a way out of the dilemma physics had gotten itself into. He suggested that the idea in Schrodinger's equation that wave function or psi represents a probability wave is all wrong. As we have seen, if it is a probability, then one has to decide when the physical world makes the transition from potentialities to the real stuff. One has to decide when state vector collapse occurs, and that brings the onus of an observer into the sanitary world of physics. Everett proposed that instead of things going from potentialities to actual events, every one of the possible states really occurs. He suggested that every time two objects interact, all the possible states that might occur actually do occur. This means that every time two electrons, for example, collide somewhere in the universe, the total universe splits up into 2, 3, or an infinite number of copies, so that there will be at least one universe that will go into each outcome that Schrodinger's equation described. If we make that assumption, if we say that when the Schrödinger equation says there are two possible outcomes for an interaction, It is because the universe actually splits into two totally independent universes, complete with two copies of ourselves. Then, in one universe, one copy of myself will see the first outcome described by the Schrodinger equation, while the second copy of myself sees the second outcome. If we do this, if we simply take what the Schrodinger equation says literally, then we will not need to invent observers to bring about the state vector collapse. We will not need to talk about state vector collapse at all. The measurement problem will just go away. Everett's idea presents us with what looks like an incredible solution to the measurement problem. It appears to get rid of the problem of invoking conscious onlookers into the world. All we need is the Schrodinger equation itself, and we need have no worries about state vector collapse. It does, of course, ask us to believe that the entire universe is constantly splitting up into copies of itself. Everett's idea has gained a lot of support in the physics community, to say nothing of inspiring a lot of science fiction stories, with scenes of Captain Kirk looking on as the denizens of two parallel universes representing good and evil struggle to destroy their other selves while becoming trapped forever between their two universes. But of course, Everett's idea says that there could be no contact between these several universes once they have split up. There could be no way whatsoever to prove that these other universes exist. There could never be any contact between them. The universes split off, and those universes in turn split off, and the process continues in an infinite proliferation. But Everett's interpretation says a lot more. When two electrons collide, they do not complete their interaction in an instant of time that leads to two possible outcomes. As we saw in the last chapter, the force between two electrons is caused by the exchange of many virtual photons, so every possible combination of photon interaction, including the virtual creation of electron pairs and other particles, must be included. This means that every interaction of two electrons must lead to an infinity of universes. Moreover, these two electrons do not have precise positions and speeds. The uncertainty relations tell us there are an infinity of possible initial states and, for each, an infinity of outcomes for every pair of particles in the universe. The number of universes splitting off in one single second is not simply non-denumerably infinite. It turns out to be one of Cantor's alephs of superinfinity numbers. The result is that our universe of universes would be piling up at rates that transcend all concepts of infinitudes. Mathematicians have found that there are different kinds of infinities, whereas the infinity of the ordinal numbers 1, 2, 3, 4, 5, 6, 7, etc., and the prime numbers 1, 2, 3, 5, 7, 11, 13, etc., are both of the same type and both just as infinite. Some things differ as to just how infinite they are. Using the ordinal numbers, one can count how many prime numbers there are just fine. Even though they are both infinite, one can nevertheless proceed on the infinite task of counting them. The counting process is quite definable and orderly. But now I try to count how many points lie along an inch-long line. Well, no matter how you try, the effort is doomed to failure. You cannot even get started in an orderly fashion. This shows that there are at least two kinds of infinities, but mathematicians have shown that there is an infinity, a countable infinity of these types, and the designation of these types is given by their aleph number. The original work was done by the German mathematician Georg Cantor, who gave these infinities their designations in terms of the aleph symbols. As a result, they are also often called the Cantor numbers or infinities. Despite this, many physicists would still prefer this Everett interpretation, just as long as it keeps what they feel to be the metaphysical nonsense of consciousness out of physics. But the Everett interpretation does not, in fact, work. This has only slowly become clear to me and to other physicists. There are two major problems with the many worlds interpretation. Let me show you what these problems are. Let us say that we have an experimental apparatus that enables us to look at an individual atom as it radiates away some excess energy. The way we run the experiment is to press a button that flashes a high-intensity ultraviolet light source at the atom, and then we wait with our light detectors to see which of two possible photons come out. A high-energy photon, say of blue light, or a low-energy photon, say of red light. Quantum mechanics will tell us just what the probability is for each of these two possibilities. Let's say that the probability for the blue photon is 0.9, or 90% of the time we get a blue photon, and 10% of the time we get a red photon, a probability of 0.1. Now let us do a sequence of 100 experiments with this apparatus. Quantum mechanics tells us we should expect 90 blue photons. Probability theory says it is unlikely that we would see fewer than 85 and less than 1 chance in 1,000 that we would see only 80 blue photons. But if we follow Everett's idea about the universe branching at each event, then after the first event, there will be 2 of me and 2 of you looking at the results in our respective universes. One in which a blue photon was measured and one in which a red photon was measured. After 2 experiments, there will be a blue-blue world, 2 red-blue worlds, and a red-red world. After 3, a blue-blue-blue world, 3 blue-blue-red worlds, 3 red-blue-blue worlds, and 1 red-red-red world. If we are in the red-red-red world, we should be a bit surprised. Quantum mechanics says there was just 1 chance in 1,000 for 3 red photons to turn up in a row. But using the many worlds theory, we have 1 chance in 4 of being in that world. By the time we have done 10 of our experiments, most of the universe will contain surprised yous and me's. By the time we have done all 100 experiments, the chance that we will be in a universe that gives results consistent with Schrödinger will be 1 in a trillion. There are ways of patching up Everett's idea. One of these ways was suggested by Everett himself. We assume that there is a greater chance for us to take the blue branch than the red branch. This tack, however, does not work. There are 2 branches. Each is occupied by copies of us, or else all we have is different language, different words for this idea of potentiality. If no universe appears for one or for the other of the possibilities, then that branch was only a potential event, and we are simply paraphrasing the Copenhagen interpretation, nothing more. There are ways to patch up Everett's interpretation that will, in fact, work. We can say that for each event, there are an infinite number of blue universe branches and an infinite number of red universes, and that, furthermore, for each and every red universe branching off, there are 9 blue universes. This works. It raises us 1 notch higher into Cantor's superinfinity count. That is bad, but it is not the real problem caused by this modification. The problem is that we now no longer have a simple interpretation of Schrödinger's equation as originally promised by Everett. The solution to Schrödinger's equation do not have terms expressing infinities like that. We would have had to invent a special way of handling the Schrödinger equation in order for things to turn out looking the way we see them. We would have had to add new hypotheses to quantum theory that do not buy us anything that can be put to the test experimentally. A greater difficulty comes from the fact that Everett really does not tell us where or when the universe branches. If As is frequently done, we talk about the branching of the universe occurring when we make an experiment. When we look to see whether we have a blue or red photon, then we are back to hypothesizing a conscious observer to define when this branching happens. Again, we have made many new hypotheses and we have gained nothing. If, however, as is usually thought, if not explicitly expressed, the branching occurs after interaction, then we wind up predicting the wrong physics with Everett's many worlds hypothesis. Look at the double Stern-Gerlach experiment we talked about a moment ago. Branching after the electron interacts with the first magnet leads us to expect the wrong results coming out at the end of the second magnetic field. Remember that if the universe separates after the electron passes the magnetic field produced by the electric current, then the Schrödinger equation should not contain two terms for the right and left orientations of the atom, but only a universe with a right pointing atom and a universe with a left pointing atom. When the atoms pop out at the end, there is no longer any reason for it to right itself and become an atom pointing up. Instead, half should now point up and half should point down as we sit in one of the now many universes that see a stream of atoms coming out. This part of Everett's many worlds interpretation works only if we keep the observer or keep the idea of measurement somehow as part of the formalism. But why should we not actually want to keep the observer in the picture? Why should we not see the occurrence of this necessity for a conscious observer in quantum theory as something that tells us about the nature of reality? After all, conscious observers do exist. So far, nowhere else in all of science have we seen anything that gives us any hint about what consciousness really is. Maybe this Gordian knot is simply something we have created in our own minds because we cannot see the simple solution. Hidden variable interpretations. Now let us look at the fourth kind of interpretation of quantum mechanics. You may have picked up on a salient point of this whole measurement problem much earlier. Sure, quantum mechanics has had its successes, but isn't it being just a bit presumptuous to believe that no future theory will alter the basic scheme of quantum theory to explain what really lies hidden behind its outwardly random behavior? That is surely what Einstein was saying. Heisenberg gave us reason to believe that any hidden real position and simultaneous real velocity for an electron was impossible to know by present methods. But maybe tomorrow's methods will change this. Or maybe if we could only look behind the veil of this random behavior, we would see some microscopic engine within each atom, within each particle that generates such a complex behavior that it looks to us like a non-deterministic reality, a randomness stamped on all atomic events. If such a hidden machine exists in each particle or governs the stochastic behavior for every collection of objects, then knowing its internal workings and settings, like knowing the key to a cipher, would allow us to read nature's hidden messages. If such machines do exist within the atoms, then they must have hidden parameters, hidden variables that are like the key to some baffling cipher. Such a picture of the inner reality that might lie hidden behind quantum mechanics has been referred to as a hidden variable interpretation. Hidden variable proposals began with de Broglie, you will remember, first showed that particles of matter, that is, ordinary objects, have a wave-like property, just as light waves have a particle nature. De Broglie's idea was that all matter exists as discrete chunks or particles that are guided in their motion by waves. Particles, electrons, protons, atoms are like surfers carried along on a wave. As a consequence, their behavior is in part determined by the wave motion, but it is also in part chance behavior because no one can say just where along the wavefront the particle is surfing. But de Broglie's idea was swept away by another wave, the tide of quantum mechanics advancing with the equations of Schrödinger and Heisenberg and with the ideas of Born and Bohr. The idea of a hidden mechanism responsible for the statistical behavior of atomic matter seemed an unnecessary encumbrance for a theory meeting success upon success everywhere it was applied. Physicists are pragmatic to a fault. Why put aside something that works for the sake of what may be only a philosophic nicety, especially when the theory in question is working everywhere we turn? After all, de Broglie's ideas might offer a way of visualizing some hidden workings of quantum mechanics, but at the expense of reinstituting a classical conception of reality for the physics that was progressed beyond such limitations. This alternative has not appeared attractive. De Broglie's ideas were all but forgotten when Bohm in 1952 again attacked the problem of explaining quantum mechanics in terms of a quantum field, a field much like de Broglie's guide wave. Bohm, however, pictured the particles as having an entirely conventional fashion. Bohm pictured these particles as following Newton's equations of motion, but he assumed something else was going on. He assumed there was a new kind of force, a rapidly fluctuating quantum force jostling the particles about. For Bohm, the quantum world was a veneer covering a deeper, hidden world that could be understood without notions of potential states or conscious observers. However, this hidden variable conception of quantum mechanics did not work as Bohm had hoped. Physicists quickly pointed to flaws in the approach. After all, Bohm had not given us a new equation for quantum mechanics. He had only renamed portions of the Schrödinger equation. His quantum mechanical force field, as formulated, was simply the collective effect of all the potential states of the particle. The change Bohm had proposed was no more than a relabeling. When you got down to brass tacks, his theory worked just the same quantum way. In fact, though he spoke of a hidden variable theory in which new effects taking place on a subatomic level would be the cause of the quantum staccato, Bohm had not even provided that. Bohm's effort to take physics back to a more comfortable classical way of visualizing atomic reality failed, but Bohm did give impetus to the idea that some additional process somewhere must be taking place. Every time we carry out an experiment to measure what the atoms are doing, we get a different answer, an answer taken from that statistical description of quantum mechanics, all right, but still a different result each time. What is responsible for each measurement's particular result? Are we indeed, as Einstein had charged, merely looking into the eyes of a God who would play dice with our desires and answer our quest for truth with noise? Although Bohm's quest was surely a good one, to advance our understanding of the causes of the quantum stochastic nature, it was fatally flawed by his desire to return to those glorious days of yesteryear, a time of certainties when matter was matter and waves were waves, and it received the appropriate reception among the scientific community. For Bohm to have been correct, his variables would have to have had a mechanism within each particle or guiding each particle that would determine the outcome of each atomic event. But other scientists were bent on showing that such ideas could never work. A succession of mathematicians and physicists went to work on the basic ideas of quantum mechanics to show that the concept of potential states Potentialities could not be eliminated from quantum theory without totally altering its predictions. That is to say, if we begin with the fact that quantum theory and quantum experiments agree, then there is no way to remove the use in quantum mechanics of simultaneously existing potential states of the kind we referred to in discussing the double slit interference experiment without totally changing the theory and losing agreement between theory and experiment. This seemed to be the death knell for all hidden variable theories and an end to aspirations for any deeper understanding of the stochastic beat of nature's heart. But the mathematical proofs were complicated, and worse, they appeared to assume exactly what they were intended to prove. The arguments revolved around something called dispersion-free states. This is the idea that quantum mechanics could be written down in some new way that would not assume a superposition of potentialities, but would assume rather that the objects or systems were in some single unknown state all along. The mathematicians and physicists working on this problem began by accepting that quantum mechanics, as it stands, represents physical systems in terms of a superposition of potential states, a collection of pictures given by psi or wave function. They would then prove that if that were so, then one could never find a new theory that did not contain a superposition as some part of the new formulation without altering the predictions of the theory. Opponents like John Bell shouted foul. They claimed that any proof is invalid that starts out by assuming exactly what it intends to prove as an essential part of the theory. Because it was assumed at the outset, they maintained it was hardly surprising that these proofs wind up showing that theories omitting the idea of dispersed states are impossible. Actually, all this was a misunderstanding. These proofs did not begin by assuming that quantum theory had to be in a superposition of states or had to be expressed by potentialities. All they did was point out that the experiments that have been done show that this is how one can represent nature. What they did was say that quantum mechanics agrees with experiment. Therefore, let us assume that the present way of expressing quantum mechanics gives correct results and then see whether it is possible to re-express these same results in a new way in which hidden variables explain the randomness we see. Thus, by assuming that quantum mechanics agrees with experiment, which so far is certainly the case, they proved there was no other way in which you could retain a perfect fit with experimental results while changing quantum mechanics into a deterministic theory. Ergo, the randomness cannot be shaken out of quantum theory. John Bell didn't believe these mathematical proofs. He believed they were merely proving what they were assuming. We showed examples of how hidden variables could explain the results seen in many experiments, seemingly negating the validity of the mathematical proofs. But something more than Bell had to offer is needed. To negate the validity of a proof that quantum mechanics is not compatible with hidden variable mechanisms, we require not just a single example of an experiment in which the behavior of some particle can be explained in terms of a hidden variable, as Bell argued, but indeed an example of a whole new quantum mechanics in which a hidden variable formulation yields the same results as the Schrödinger equation everywhere. However, Bohm and Bubb seemed to have something that would fill the bill. They had a new quantum theory based on hidden variables. They added a new term to Schrödinger's equation that would sit there docilely affecting nothing until a measurement occurred. And then this added term would take charge. It would select one of the potential states to be the final outcome at the completion of the measurement interactions and destroy all others like a mathematical Pac-Man eating up unwanted terms in the wave function picture of the world. Just which potential state would occur would still be a matter of chance, but now there would be something causing the result. There would be something that would select which state would occur. The final event would depend on the value of a hidden variable in the added term. But again, there was a flaw in this new effort by Bohm and Bubb to find a neoclassical physics. There existed nothing objective in their theory that would throw the switch to turn on the hidden Pac-Man mechanism that would enable this new Schrödinger equation to select the final observed state of the system and explain the physics of measurement. The equation would describe nature. If mathematicians have to inject this term when they want the system to go into a single state and leave that term out at other times to keep the answers correct, well, then it's just a fudge factor. If one is going to cheat, surely there are easier ways to fake the results. So it turned out that Bohm and Bubb's effort to introduce a hidden variable to take care automatically of state vector collapse did not work. In fact, there were many efforts to achieve a hidden variable mechanism that would still give the correct answers, but would remove the seeming need to have an observer determine when state vector collapse had occurred. These efforts could have gone on and on without resolving the problem, but John Bell proposed a daring new approach. He would show how to prove quantum mechanics was actually wrong, just as Einstein had maintained all along. If Einstein had been correct in his criticism of quantum theory, if quantum mechanics is incomplete in its description of reality, there must be a way to show this, and Bell believed he knew how. The experiment that John Bell conceived is now recognized as one of the most important experiments ever done in the history of mankind. End of chapter.